Sir,
Yeah.
I have to run all the cells again.
Why you don't see the data here?
I saw the data, but this combined DF complete imp is not getting imputed.
So that means you have to run the imp only. Library mice and imp. You see the right hand side the data, right?
Yes.
Right. Then you run the imp first. But change it to m is equal to 3 and max side is equal to 3. Okay. Import the library and run this. So rest of the participants, can you confirm you have run till this point?
Sir, after the class, try to share yesterday's and day before yesterday's notes and recording sessions, sir. Notes and recording sessions you haven't shared, sir. Mondays and Tuesdays.
Notes I have shared. Recording sessions I have to share. Notes is there. Check your mail. Yesterday also I emailed it as text files. See?
You haven't shared Monday's notes, sir. Which Python.
Mondays also I have shared. No, I blink. Yeah.
I'm talking about notes. No.
Notes, notes is not there. No, it's only practice session. There is no notes in that thing. No, it's only practice session. You want the practice notebook?
Yes, sir. Yes, sir. I didn't practice.
So I'll send it today. Once all of you are done, please confirm. Okay, guys, can I move forward? Guys, can I continue? Yeah. So we have done on two data sets, regression and classification. Okay, I am going back to the Bigma data. I am opening the Bigma data project. The Bigma data project we worked upon. So within machine learning, within the supervised learning, within the regression models, the primary model is your multiple linear regression that explains the relationship between, explains the linear relationship between a dependent variable y and multiple independent variables x. So multiple linear regression is an equation. What is the equation? Anybody? Y is equal to beta naught intercept plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x4 till beta n xn plus the residual or error term. So what are the various components? Y represents the dependent variable. Y represents the dependent variable. D0 represents the intercept or constant. P1, P2, B3, B4 till Bn, we call them as coefficients. X1, X2, X3, X4 till Xn, we call them as independent variables. And then Et is called error term or residual. What is the formula for residual? Actual value minus predicted value. Right? Multiple linear regression. So multiple linear regression it predicts a value. Multiple linear regressions will predict a value. So what are the assumptions? Participants, guys, what are the assumptions? Y must be numerical, continuous, closer to normal distribution, with minimum outliers and no missing values. X can be both numerical and non-numerical. There must be a logical linear relationship between y and x. Let us put as x's because they are multiple. So x's. No multicollinearity. Exogeneity, where y is dependent on x's, but x's do not depend on y. Sample size required is minimum 20 observations per variable. Anything I forgot? Then residuals must be homoscedastic. Residuals must be normally distributed. Guys, any assumptions I forgot? All right, should I move forward? All right, now let us look at the statistical interpretation of output in R. This is also very important, statistical interpretation of output, because in Python, we don't get the statistical interpretation. We only get the basic R square and intercept and coefficients, and then we calculate the RMSE. Whereas in the R, we get the complete statistical output. Now, the output which you need to look at in R are this. The first and foremost, you should look for adjusted R square. Adjusted R square must be between 0.60 to 0.95. Adjusted R square explains the amount of variance, occurring in the dependent variable caused by the model or the variables. Now, why adjusted R square? So we will get multiple R square also, which is what you get in Python, because adjusted R square responds to independent variable significance. Independent variable significance. It increases if the independent variable is significant, and decreases if independent variable is insignificant. Multiple R square will keep on increasing irrelevant to independent variable significance. So if you look at independent R, multiple R square, it keeps on increasing. It keeps on increasing even though the variables are found to be insignificant. So it is irrelevant to the independent variable significance. So it does not decrease if the independent variables are significant or not. So that is the reason why we use adjusted R square. Why we use adjusted R square? The first thing in a regression output you should check is adjusted R square. The adjusted R square must be between 0.60 to 0.95. Adjusted R square explains the amount of variance occurring in the dependent variable caused by the model or the variables in the model. In the output, we also see different types of R squares. Multiple R square will also be there. But why we choose adjusted R square is, adjusted R square responds to the independent variable significant. It increases if the independent variable is significant and decreases if independent variable is insignificant. Whereas multiple R square will always keep on increasing irrelevant of the independent variable significance. So when you check the regression output, the first thing you should always check for is the adjusted R square. Got it, all of you? All right, guys, should I move forward? All right. The second thing which you need to look for is the model p-value which lies below adjusted R square in R or significance F in MS Excel. Model p-value which lies below the adjusted R square in R, or in Excel we call it as significance F, must be less than 0.05. The model p-value which you will see just below the adjusted R square must be less than 0.05. Why? Because we need to reject the null hypothesis. The coefficients are equal to 0. The alternate hypothesis is coefficients are not equal to 0. So we have to reject the null hypothesis. We have to reject the null hypothesis. Must. Coefficients are your betas. The third is independent variables. The excess p-value must be less than 0.05. The null hypothesis is the independent variable is insignificant. Alternate hypothesis is independent variable is significant. Here, if any independent variable is found insignificant, when it is found insignificant, when the p-value greater than 0.05, remove the variable, and rebuild model again. Same is done for multiple variables. If you find multiple variables with insignificant thing, you have to remove those variables and you have to what we call as what we call is that you have to remove them and you have to rebuild your model. So the sequence is important. The first adjusted R square is met, then go to second criteria. If second criteria is met, you go to the third criteria. In third criteria, we have an option. If some of the independent variables p-values are not less than 0.05, we will remove them and we will rebuild our model. But if the first and second fail, you should not do thing. You have to go back and rework your model. All right, should I move forward, participants? Guys, should I move forward?
Yes, sir.
Okay, now these are the outputs which are there, which you need to understand. Once these outputs are understood, then only we will be able to know whether the model has perfectly built or not. Okay. So let us build a model for our data, which is our Bigma train DF. Right, we have built our data, Bigma train DF, which is our final data with all the imputations and all. Okay, so we have our data ready, Bigma train DF, on which we can build a model. All right, guys. So reg is equal to LM, linear modeling LM, item underscore outlet underscore sales tilde dot comma data is equal to Bigmart train DF. Now here tilde dot means include all other variables as independent variables. Reg is equal to LM item outlet underscore sales tilde dot data is equal to Bigma train DF. Summary reg. Summary reg. All of you got the output? Now, if you see the output in the console, you can see here adjusted R square. Adjusted R square is which is not in the range model underfitting. Right? It is not 0.60 to 0.95. As you can see here, 0.5622 in adjusted R square. Now below adjusted R square only you will see p value. So you can see the p value, the model p value, which is below adjusted R square, is less than 0.05, where we are rejecting null. We are rejecting null, that coefficients are equal to 0. So if I scroll up slightly and then see the coefficients, you can see the coefficients here, which are nothing but these estimate. These estimate are coefficients. These are the coefficients you can see here. The coefficients, item weight, item intercept, quite the coefficients you can see, none of them are equal to 0. None of these coefficients are equal to 0. You can see these coefficients, these are equal, none of them are equal to 0. Then independent variable p-value must be less than 0.05. So if you see this thing, only item MRP is significant, outlet age is significant, fat content is not significant, type is not significant, but outlet identifiers are significant. All the outlet identifiers are significant. So we have only 3 variables that are significant: item MRP, outlet age, and outlet identifiers that are significant. Rest of them are all non-significant. Only 3 variables are found to be significant. Only 3 variables are significant, which is item underscore MRP, outlet underscore age, and outlet underscore identifier. These are considered as significant variables. Rest of the variables are found to be insignificant. We will delete them. Basically, first of all, we should not consider this model because our adjusted R square itself is failed. Basically, our model itself has failed because our adjusted R square was not in the range, but for our academic purposes and learning purposes, we are just looking at the statistical output. So the first criteria itself has failed. So this is how you have to interpret the output. This is the statistical output of regression. This is the statistical output of regression. So any doubts, guys? All of you are able to run this?
Sir, if the R square is in between 0.60 and 0.95, what is the further step, sir?
Then you will go and check the model p-value. Then your model is good fitting. You'll go and check the model p-value. If it is also less than 0.05, then you will go to and check the independent variables p-values, and then you identify those variables which are significant impact and you keep them and remove the rest of the variables.
We have to remove significant variables.
Insignificant means no impact. All right. Now, one other thing is the interpretation of the coefficients. See, we will get the coefficients and we'll create a regression equation from the coefficients, right? Now, let us see what are the coefficients we got. Round, reg, dollar, coefficients, comma 2. So we got the coefficients like this. These are the actual coefficients which we got. So the coefficients which we got for the model are this. So item underscore outlet underscore sales is equal to 44,415.05, which is our intercept, minus 2.39 into item underscore weight minus 302.04 into item underscore visibility plus 15.57 into item underscore MRP minus 2003.26 into outlet underscore age plus 41.83 into item fat content regular so on and so forth. So this is the equation. I'm not typing the complete equations, but from these coefficients with the regression equation will be created, and this regression equation will be used for prediction. So from the summary of the regression output, regression coefficients are separated and an equation will be created, and these coefficients and the equation are used for predicting the values. So the mathematical sign of the coefficient is very important. The mathematical sign of the coefficient is important. So a positive coefficient indicates that as the value of independent variable increases, a positive coefficient indicates that as the value of the value increases, the mean of the dependent variable, also increases. The mean of the dependent variable also increases. Actually, this is all about that. So the mathematical sign is very important, because basically before we go to thing, the coefficient, actually, if you are looking at the coefficients, they signify, they basically, a coefficient will signify how much the mean of dependent variable changes given a 1 unit shift in independent variable, shift or change in independent variable while holding all other variables constant. Sorry guys, power went off. So power went off. See, the interpretation of coefficients. So how much the mean of dependent variable changes given a 1 unit shift or change in independent variable while holding all other variables constant. That is the interpretation of coefficient. How much the mean of dependent variable changes given a 1 unit shift or change in independent variable while holding all other variables constant. That is the interpretation of coefficient. Now, the mathematical sign of the coefficient is important. So a positive coefficient indicates that as the value of the independent variable increases, the mean of the dependent variable also increases. Similarly, a negative coefficient indicates that as the value of independent variable, negative coefficient increases, the mean value of this will decreases. So this is the interpretation of the coefficients, which you must understand. In interviews, they will ask you, what is the significance of the coefficients? Coefficients will tell us how much change in how much the mean of the dependent variable changes given a 1 unit shift or change in independent variable while holding all other variables constant. The mathematical sign of the coefficient is important. A positive coefficient indicates that as the value of independent variable increases, the mean of the dependent variable also increases. As a negative coefficient indicates that as the value of the independent variable increases, the mean of the dependent variable decreases. Guys, can you hear me, all of you?
Yes, sir.
Participants, any doubts? Guys, any doubts? All right, participants, should I move forward? All right, participants, should I move forward? Guys, you're there?
Yes, sir.
So, like I told you, visualizations are also there in regression. the residual visualizations are also very important. So the residual plots, also called as the regression plots, are very important. So let me split the plot window. MF row is equal to C of 2 comma 2. Plot reg. So basically, you get the 4 plots. The first plot is for homoscedasticity. Is this homoscedastic or heteroscedastic? That is what you have to choose. Residuals versus fitted. The first plot you should check for homoscedastic or heteroscedastic. I have already shown you the graphs couple of times. Homoscedasticity versus heteroscedasticity, how the plots look like. So if I go to the images of homoscedasticity and heteroscedasticity, you can see here a satisfactory model and an unsatisfactory model plot. A satisfactory model plot will be in a narrow range, left to right, whereas an unsatisfactory model will have what you call in a flower bouquet pattern. It will be in a flower bouquet pattern, heteroscedasticity and homoscedasticity. So either the plot should look like this. This is the homoscedastic pattern. This is the heteroscedastic pattern, which is a non-satisfactory model. Now, what do you see in our data? In our data, we see a flower bouquet pattern, which indicates heteroscedasticity. See, this is not like a thing, it is a heteroscedasticity. And normal Q and Q plot, most of the observations should be on the dotted line. But you see, large number of observations are away from the dotted line. See, from this, these observations are away from the so this is a heteroscedastic pattern, and you can see all the observations are moving away from the dotted line, which indicates the residuals are not normally distributed. This plot tells us that residuals are not normally distributed. This plot indicates heteroscedasticity, which tells us that so residuals versus fitted is indicating heteroscedasticity.
It is homoscedasticity, sir.
It is heteroscedasticity. How can you say it is homoscedasticity? Homoscedasticity means it looks like this. Narrow range, left to right. Hmm. So what is homoscedasticity and what is heteroscedasticity? What do you see in our model? Do you see this pattern or this pattern in our model? We see this pattern, right? Flower bouquet pattern. So heteroscedasticity. In narrow range, parallel between two lines is homoscedasticity. So this is heteroscedasticity. Where how can it be homoscedasticity? Which is not good. Similarly, normal Q and Q plot indicates residuals not normally distributed because most of them are not on the line. They are away from the line. As residuals are away from line. So these two plots will be very important for regression analysis, which are telling us our model is not a fit model. Our model is a underfitting model. To get back our model back, we use the plot window back, we use dev dot off. So whenever you split the window, you also have to run the dev dot off to get the window back to the normal state. Dev dot off. Got it, participants, all of you? Guys, all of you are there?